Good morning. Art's kind of call my comments typically thoughtful. I find them typically orthogonal to whatever the workshop subject happens to be. And I suspect this morning will be no exception, especially because I was looking at the Wordle as to where the papers went. And I didn't see, I saw in very small font what I consider to be the heart of this issue, which is the people issue and the communications issue. And that's kind of what I'm going to be talking about, I think, this morning. That this is, at heart, an issue about how information flows to an enterprise, which is fundamentally about how people share information, which is fundamentally about storytelling. So I'll come back to that. I first want to start by applauding both Stevens and the CERC and COSI for tackling this challenging, somewhat amorphous, but critical intersection between systems and software engineering in different ways. I was thinking as I typed these notes up on the train yesterday, this has been at the heart of what I've been doing for 7 years since I joined Lockheed Martin, even though I didn't really know it much of the time. But as I started to put these notes together, I realized this is sort of an existential topic. And so I really applaud you all for taking it on. This is an august group. I looked at the list before I came. Many of you I've worked with. Many of you I know just by reputation from having attended some of your webinars and read some of your papers over the years. So I know good things will come out of this. I'm sure one day we'll look back on this as a seminal workshop in advancing this important topic. Just, I guess, kind of to state the obvious, despite how critical this intersection is, it's really poorly understood, in my opinion, and it's poorly articulated. And that leads to great challenges, both, of course, in engineering education, but also to my day job in engineering practice. You know, how do you organize people and programs around complex systems, which is fundamentally what Lockheed Martin does. We're a large-scale system integrator of complex systems, software-intensive systems typically. And so this is a really important issue to us. What I want to start by doing is telling you a little bit about how I came to my job, not because I care to read my bio to you, but because it will give you a sense for the perspective that I bring to the question that you asked me to talk about. And I want to kind of put that into 3 spheres of engineering that I have been in or around, one being systems, one being software, and one I'm going to call traditional, for lack of a better word. I went to school. My master's is in electrical engineering, my undergrad in biomedical engineering, got out in '88, in really a traditional electrical engineering, Maxwell equations, scattering theory, solving triple integral kind of engineering background, pretty straightforward, stochastic processes and so forth. Went to work on radar systems, antenna theory, where I got to apply all the things I learned about propagation and stochastic processes and so forth, and spent probably the first 4 or 5 years of my career pretty much at my desk, pretty much on my computer, back then my IBM XT, because only the important people got the AT. So I got the XT. And just working in very traditional engineering. And so I grew up with that perspective on the discipline. And then I found, as I worked my way to higher and higher levels of a radar system, from antennas to propagation theory to signal processing to transmitters, receivers, eventually you got to the point where you started to call yourself a system engineer, a radar systems engineer, which is where I kind of spent the bulk of the technical part of my career. And I didn't think about it, you know, most as you get older and you get nostalgic and you start to put your career and life into perspective, didn't think about it, but it was really a fundamentally different shift from what I'll call traditional engineering. And again, the biggest difference between the two, just from how I spent my day perspective, was you spend a lot more time talking to people as a systems engineer. You know, as an electrical engineer, a mechanical engineer, a chemical engineer, what have you, in those traditional disciplines, again, you're mostly solving problems by yourself or in small teams. As a system engineer, you're talking to customers constantly because your job, in many senses, is to be the voice of the customer for the program. You're talking about things like budget, which never came up before. You're talking about sustainability of the system, how you're going to get these particular parts, legacy, reuse. You end up in a whole different world. But again, it's sort of fundamentally distinct in that you start dealing with people. And so that was my first 2 experiences, what I'll call traditional engineering and then systems engineering. Then I came to Lockheed Martin 7 years ago to run something called the Systems and Software Initiative. And that initiative was created because there were a lot of problems which were coming to the fore that were manifesting as software problems. And those are all in the newspapers, and not just Lockheed Martin, but every company with software challenges. And the CEO then at the time gave my boss, our CTO, the challenge, look, this is important, whatever it takes, let's solve this, create an initiative, put money behind it, put a vice president behind it, and I was hired to do that with the objective, which was written into my performance review, of eliminating all software problems on Lockheed Martin programs. And I was naive enough to think, okay, let's do it. And launched out, had the pleasure early on of meeting Cheryl, who was then in one of our lines of business as a software director, who very patiently over the years after that, basically said, you think you're tackling software problems, but that's a symptom. You know, you're treating a symptom of what are typically systems problems, or program management, which is a fine distinction, or challenges at the interface of design. I think Art made a joke related to, you know, it's software is where people always think you can solve problems that are created anywhere else. So it's kind of at the end, and it's a manifestation of something that happened much earlier. And so that realization became clear to me over time, and so that's kind of where I got into this world of software systems and software-intensive systems as distinct from systems engineering, and started to think about this issue of what is the nexus between those two disciplines. Another observation I'd make, which isn't one of the three spheres here, but after I began what Norm Augustine calls my descent into management. It doesn't say about me, it said that about himself in his book. I got into, from systems engineering, I got into program management, which again is a fine line. In a sense, systems engineering started out as a program management discipline, not really an engineering discipline per se. And from there into profit loss management, I ran a line of business at SAIC. And so I've also got a lot of experience at enterprise organizational design and enterprise structure. And one thing that I like about what Stevens did when they formed the School of Systems Enterprises was they put those two words together. Many of you are tired of hearing me say this, who hear me speak a lot, but I'm fond of quoting from Conway's law, which is that any organization is constrained to produce a system which mirrors its own organizational construct. And I believe that's fundamentally true because I've seen it happen. You know, from day one, when you have a meeting to decide what system you're going to develop, who's in the room determines what that system looks like. Who you team with determines, you know, work share and what the system ends up being. So that's a long way of looping back around to my comments that fundamentally this is a communication issue in my mind. So what I'd like to do with this is, again, talk to these three spheres in such a way, you know, I honestly, when Art asked me to keynote this topic, I didn't know where to start, and I still don't know where to start. But I thought what might be useful is to tell you how I see systems and software engineering as distinct from traditional engineering and like each other. So if you picture those three spheres and draw a dotted line around systems and software, what I'd like to talk about are 7 or 8 areas where I find them to be very similar and distinct from traditional. And my hope is that might illuminate some sort of a path forward in terms of thinking about, from an education perspective and from a practice perspective, how do we combine those two different disciplines. Make it just a couple observations, which will sort of be stated in the obvious to this group, but one fundamental difference with traditional engineering is it's fundamentally constrained by physics, which is distinct from software and distinct from systems. And that really drives a lot of how we think about those disciplines, be they electrical, mechanical, or chemical, or biomedical, or what have you. At the end of the day, you can only do what the laws of nature say you can do. And so that gives a different mindset, a set of constraints to those disciplines, because you're working within a constrained world, and that gives you a set of tools and practices and a language which is very much, keep using the word constrained, and slowly evolving. That's not to say they don't evolve. You know, new materials impact mechanical engineering, certainly. So disciplines do all evolve, but really slowly compared to software, certainly, which has been having a hard time keeping up with Moore's law, among other challenges. And so they're much more manageable disciplines, if you will. Systems and software, I would argue, I don't think controversially, are both challenged or, I'll say, in trouble in different ways. We had, some of you were at CSUN this week. We were here. I was moderating a panel, and one of the speakers was Dr. Al Jones from NIST. And the task that I gave the panelists was to say, what do you see as the gap in system engineering in terms of addressing systems engineering, in terms of addressing complexity? And his last takeaway was basically, we're nowhere when it comes to thinking about systems engineering in the face of complexity. This discipline has evolved. These are more my words than his at this point, but discipline has evolved over the last half century and tried to add layers of process and tooling to what it does. However, complexity has been so far out in front of that those layers of extra rules and practices have not kept up. And so his takeaway was, you're going to need a fundamentally new approach to how you think about systems engineering, and I think that's true. So, and software, of course, its woes are well known. I'm not sure if they still do it, but a few years back there was something called the Chaos Report that would come out and talk about how many software jobs that start, A, don't finish, which is a large fraction, or B, come in late or well above budget, and it's just about all of them. It's something like 90% all end up above budget and late. Things you see constantly in the news, like the rollout of the healthcare website, for example, something that should have been fairly straightforward to those sort of websites. It's always hard, and it's always expensive, and it's always late. So clearly there are challenges in software that both academia and industry and government need to figure out how to tackle. So again, what I've taken here is kind of a compare-contrast approach to finding some commonalities between systems and software. And again, I think there's 6 of these, and I'll try to move through them expeditiously. The first observation I'd make is that both have a workforce that varies tremendously inside a given organization. If you ask me, Jeff, Lockheed Martin's got 60,000 engineers and technologists. I think our largest is mechanical engineering. If you said, Jeff, bring me 100 mechanical engineers and line them up on the stage and talk about what they each did, it would all be very, very similar. They would all kind of have the same types of backgrounds. They work in the same types of problems, speak in the same language, same for electrical or any other traditional engineering discipline. But I could go and get you someone coded as a systems engineer at Lockheed Martin, and I'm sure this is true everywhere else, who at the one end could be a chief engineer who is very experienced and grizzled and has seen a lot and knows what can go wrong and knows where every one and every zero and every component is on their system because they've worked something like, I'll say, or pick any major system forever. That's a system engineer. I could also bring you somebody that's probably 6 months out of school whose job is to manage storage database, and he's also called a system engineer, he or she. And so there's a tremendous diversity in that discipline of what we call a system engineer. Software is the same way. I could bring you someone that's done embedded architecting of a highly complex high throughput radar processor who's a software engineer by code. I could also bring you someone, again, who's 6 months out of school, who's an app developer, who's coded as a software engineer. So we don't have a real homogeneous group of folks in either one of those disciplines, which is different than traditional engineering. So I would, and I tried to end each of these sections and notes with something productive in terms of suggestions that the group could work on. And I'm not entirely sure what to do with that one, so I just leave it for you to kind of put in the back of your brain. The second thing, which is a little bit different, I think, between systems and software and traditional engineering, is that the architecture is paramount. Now, you can argue a radar architecture is certainly paramount as well, but it's fairly, as someone that came out of radar, straightforward. There's transmitters, there's receivers, there's antennas. There's only so many ways to put together that. So while the architecture matters, most of the energy and time spent is in the development stage. It's getting the antennas bent just right and getting everything done. Systems and software, to my way of thinking, the architecture is the most important piece. And because architecture is where you first decide if you're going to manage complexity or not. The architecture is the one chance you get to say, I appreciate the gremlins that can come out of this system, and I'm going to architect in such a way that I manage them. And I'm always very cautious about the power of complexity is the capability it gives you. It's not a bad thing. Complexity should be embraced for the capability that it can create. But introducing unnecessary complexity in terms of things like how you lay down your code on an architecture, which how you deal with things like clock jitter. You can reduce unnecessary complexity in your architectures if you're smart about it. But all too often, we don't spend enough time on the architecture. So as a thought for both education and what we've tried to do for practice is focus on the architecture for our systems and software code. Probably the most long-lasting thing, long-lived activity that started with the Systems and Software Initiative I mentioned 7 years ago was something called the Joint Architect Working Group, the JOG, which meets every year. It is systems and software architects together. It's one of, if not the most enjoyable of our many workshops that I go to, because they are like-minded despite being from systems and software. They are asking the same questions, people questions, customer questions. They are in many cases philosophical questions. My favorite architects have philosophy degrees as part of their portfolio. It's a thoughtful group, necessarily so. And so as you think about the future of these two, system and software interface, I would suggest architecture should be prime. So the third thing, that was the second one. The third thing is, at the end of the day, as I said, this is all about people and how they communicate. In software, you're typically creating a user experience of some sort, whether in Lockheed Martin's case, it's an FAA flight management system or the census or what have you, or whether you're, again, doing a user interface for a customer, a website. It's really all about the user experience that you create. System engineering, similarly, is all about the user experience. When we meet with customers, potential customers, to say, talk about the evolution of a system, whether it's an aircraft or a ship or a radar or what have you, that conversation with the customer is the most important thing. It's up front. So it's all about that communication. I've often said inside the company, one of my jobs is to oversee the risk process that assesses red, yellow, green programs and problem programs. I have never seen a red program that was not red because of poor communication at the end of the day. Every problem in my mind has stemmed from poor communication of some sort, the right people not having the right information at the right time. And so as you think again about what's in this overlap between systems and software, I would suggest communication. It's not typically, I don't think it was on the Wordle, and I don't know that it's in any classes of software, but being able to communicate clearly both inside the company and with customers is not so critical to the electrical engineer like I was working at their computer. It is critical to both software and systems people. It's just fundamental, and it should be a part of whatever you consider as the overlap. The fourth thing is how you test is absolutely critical. Again, with a radar system, just to come back to the example, I know test is certainly important, but it's sort of a foregone conclusion. You've got a requirement to develop a radar system that has a certain detection range, and you can detect that detection range. Pretty straightforward. When you look at systems and software, having a clear understanding of what and how you'll test is critical to success, and it really should drive design, and too often it doesn't. We still have a mentality that test is the thing at the end with the person with the clipboard is saying, yep, 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 yep. And again, there are some traditional engineering disciplines where that works. In systems and software, I would suggest you really ought to be starting with tests. How am I going to test this? How is this going to be seen as a successful system to my user? And tests should drive architecture and design. It shouldn't be the thing at the end, which is an afterthought. So again, as you think about the overlap, I would suggest putting tests in there. Similarly, integration needs to be taken seriously. And traditional engineering integration, again, because this is constrained by physics, certainly challenges often with meeting a cancellation ratio in a radar system or what have you as you put boxes together. But at the end of the day, you're putting boxes together and staying up late. You can pretty much always make it work. Systems and software integration is where you really have, it's where you find your problems. It's not where you want to find your problems. You want to find your problems, much earlier on. And all too often, we don't take integration, we collectively as a community don't take integration seriously. It's just, okay, now we'll put it all together. Well, no, because in a complex system, when you put it all together is when the gremlins do emerge. And so integration, system integration and software integration, like architecting, like test, I think should be at the heart of any program to successfully tackle the overlap between systems and software. COTS integration and software, everybody thinks is easy, and so, these are all stuff off the shelf, right? Just put it together and then package it and deliver it. It's never easy. It's always hard. Again, coming back to even something like the healthcare website, just because it's in the news this past year, it's really hard to just put things together and all of a sudden have them work. And you've got to budget adequate time for integration. You've got to take integration seriously. And I worry that all too often it's not. I don't know anything behind the healthcare website challenges, but what I read was there was not really a strong integration function. That the plan was they would have different pieces and they would just come together. There's a science to system integration, okay? It's not just putting stuff together. There's a science that needs to be codified and studied and taught when it comes to systems and software integration. And it should be a key part of this interface. Next, again, I've already said this, but it's worth saying again, the customer is front and center in these two disciplines. So the electrical, the mechanical, the biomedical engineer, and again, I'm overstating things for effect in an attempt to draw some distinction. The customer is somewhere else. My customer, when I was a radar, from the technical side, traditional engineering, was always somewhere else. But the customer is front and center for both systems and software. And one of the things that we're working on as part of a broader customer relationship strategy is teaching engineers active listening. People think that you can just say to your customers, what is it you want, and you'll hear, but you won't. You got to figure out how to ask the right questions. You got to figure out how to listen. You got to figure out how to sort of pulse and then sit back and be quiet and listen. We're not really good at that, I would say, as a broad Myers-Briggs type when it comes to engineers. But it's a skill that can be acquired, active listening, and should be acquired, because that's really when you understand the customer intent and what is it that they're going to want to do with this system. And so I'd encourage that, even though it's a touchy-feely soft topic like communications, to be part of a program which is at the overlap of systems and software integration. I'll make an observation that'll sound odd and not certainly arguable, but from what I've seen, there is more of a diversity, in particular a gender diversity challenge in software and systems than in traditional engineering. Now, clearly electrical and mechanical have a gender challenge as well. Software is particularly concerning because in the 70s it went from something like 36% women, and now it's down to, I think, 15 or 16%. And if you look at the number of high school girls taking AP Comp Sci, for example, it's minuscule in percentage terms. I think, and systems engineering similarly, I've never seen statistics on system engineering, and I'm just speaking to gender, but I'm sure it's a broader diversity challenge. But I was at last fall, the NDIA System Engineering Conference, and I made a point. There's probably 400 people in the ballroom. I made a point of counting. I think there were like 9 women there. And I also looked at the program, and I made this observation from the podium when I spoke, that every speaker was male, and there were like 20 or 25 speakers. Again, these are communications and people issues at heart, in my opinion. And if you don't have a diverse set of developers developing the solution, you're not going to be adequately addressing the diverse set of needs of the user community. I think it's that simple. So the challenge there is, if I were, putting together a program to look at the overlap between systems and software, I would focus on asking at least the question, what are we doing wrong that we're not attracting more women and minorities into these two fields? And I think if you address the question, or at least ask the question, it will highlight things that need to be highlighted anyway. There's work done. I was at an event at the White House a few months ago on getting girls to go into STEM, girls and women in STEM professions. And there was a professor from Stanford, and I forgot her last name. First name was Joe. Was talking about how women learn versus how men learn, and talked about the importance of a problem-centric approach and a collaborative approach, and what am I going to do with this being more important. And I don't know, not an expert at all in that field, but that's a systems thing that we we should be teaching. And if we're not teaching it that way, then we're not going to draw a diverse set of folks into the field. So I think it's a win-win in many ways to address the diversity challenge in both those fields. Another observation that in both these cases, the environment is changing more rapidly than the practice. Again, that's not true in electrical, mechanical, or others. You can keep up with the change. Software is just changing so fast that attempts to just keep up with it, with that practice, are, I don't want to say impossible, but they're really, really hard. And similarly systems, because the systems landscape changes with things like the federal budget, in my case, as to what the customer is going to want with the threat environment in our case. What threat are you actually developing a system for? That used to change over decades. When I started working in the late 80s, it was Soviet threat, and it was the Cold War, and the threat every morning is the same. You go to work, and it's the same systems you're developing for the same threat. That doesn't happen anymore. The threats change almost on a daily basis. This morning's headline in the journal just surprised me because it almost seemed to come out of nowhere, and all of a sudden you've got which was related to trouble in Iraq. So threats change quickly, so the systems have to change quickly. The observation I would make there is traditional engineering, the academic industry model, I think works fine. You in academia, taught me Maxwell's equations, and you taught me stochastic processes, and all that's well and good. I had these tools, and then I went to work, and then I worked on a radar, my first job, and I actually saw how these ones and zeros coming off of this A to D converter related to what I learned in those classes. And then I could move on through my career. So it was supply, demand, sort of natural progression. I suggest with systems and software, we need to find new ways to work together. So that's why things like the CERC and the Center for Complex Systems and Enterprises that we're proud to be the founding sponsor of here at Stevens are so important. You need to figure out work-integrated learning if we're going to tackle systems and software on an ongoing basis. You're not going to learn and then go do. It just isn't going to work that way. Something like cybersecurity, for example, you really learn that by being attacked. You learn that by sitting in a network operations center and saying, wow, this is happening, and it's changing. What am I going to do with it? There's some basics you learn in school, sure, but you really learn when you're being attacked. And so you need to figure out an iterative approach to this lifelong, integrated, iterative learning. So that's a challenge I'd put for our collective community. I know I'm running out of time. I think I just have two. I do just have two. And they sort of got increasingly odd as my train was close to pulling into Penn Station last night. Both of these, in my mind, embrace what many call the auteur theory of personal vision. If you're a fan of films, there's a theory called the auteur theory, which has been around, I think, for about half a century, which basically says a film reflects the vision of its director. The director sees a Citizen Kane, and then everything else just comes into play and is coordinated in order to cast that vision onto the screen, and that's your user experience. That's come under fire in recent years, among others, from writers and actors who say, no, we also create the user experience. And I have no opinion on any of that, except to say, my observation, if you look at people like a Kelly Johnson, who founded Lockheed Martin Skunk Works, or Steve Jobs, who I would argue was a system engineer despite not having such a degree, that's a strong personal vision. That's an auteur vision, which has been manifested in a system, Kelly Johnson's aircraft, for example. I think systems and software both kind of embrace that. Traditional engineering does not. Traditional engineering is, again, small teams of folks working on a problem, and it's kind of faceless. And again, I'm not sure what to take from that, except the observation that successful systems and software engineers are different than successful traditional engineers. They tend to be people that break the rules in certain ways, and that's a good thing in certain ways. They also tend to be folks, Kelly Johnson had his rules, which you can find on the web. There's only a handful, I think there's 10. Steve Jobs, when he came back to Apple, famously wrote down all the products on the whiteboard and crossed out most of them and said, no, we're going to do just these 4 things. Having a small number of rules, but having them be inviolable, I think is important for success in both systems and software. It's also how nature works. If you look at complex natural systems, you can describe them with very few equations. right? Like weather, you can describe with very few equations. And those rules are inviolable, and there aren't that many. However, they're critical in order to realize a successful complex system. And then lastly, and this is a related observation, which is, I'll read it as I wrote it, the spread in impact between good and bad practitioners is significant in systems and software. Again, if I put those 100 mechanical engineers from Lockheed Martin, there's better ones and there's worse ones. It's a distribution, but it's a pretty tight distribution. You know, to get to that point, you know, you passed the right courses and you worked in the field, and you can all work together on a team, again, despite some distribution of, I'll call it capability, because it's a pretty tight distribution of capability. Whereas in software, I've seen interesting studies that speak to the tremendously positive impact of, first of all, the diversity of ability in software engineers, as well as the impact that a really good software engineer has, or a really bad software engineer has on the outcome of the system. You know, one bad mechanical engineer will be covered by the practices and the tools and the team. One bad software engineer working in isolation is going to do things in that code that is just going to bring the system to its knees at some point. So somehow this notion of, this is always on my mind given my day job, this notion of competency and the spread of competency and understanding the degree of competency, which kind of loops around to my first point, that there's just so much diversity. It's not a homogeneous group for systems and software, is important to figure out. So, in summary, I would say these are, to my way of thinking, these are both relatively new disciplines, right? Systems and software. Traditional engineering is over 100 years old, typically. And both are sort of grafted onto traditional engineering in somewhat of a kludgy fashion. System engineering evolved as a program management discipline to tackle how do you manage large, complex programs, and then we brought it into the engineering community over the years. Software engineering, when it first came up as a term, had a question mark after it. It was sort of, is this engineering? And there's still people that have that argument, is this engineering? I would say both systems and software are part of engineering. And we need to take responsibility for that and accountability for that and figure out a way to incorporate all three of these spheres of engineering, because if we don't, nobody else is going to. I've worked 25 years now, enough to see there's no other function that is going to take on the responsibility for what the Nkosi definition of systems engineering is, which is the successful realization of systems. That's an engineering job. It's an engineering with a small e as well as an engineering from a professional degree perspective. I think I am going to stop there because that gets a little bit repetitive. The things then that I came at, if I were doing my wordle, were communications, testability, architecting, integration, organizational design, impact, customer, work integrated learning, and people over technology, which is, again, when I first came up here, I tend to be orthogonal to where Art or Dinesh asked me to go, I think. But I wanted to just share what I hope are maybe a little bit provocative and a little bit out of the box thinking on the challenge before you. And I want to thank you all for taking on the challenge. I really do believe this is a really important event, and I really believe it can be a seminal workshop that one day folks will look back on, like they looked back on the gathering of the first Agile community, 10, 12 years ago, and say something happened there, something came out of that, which then built into a movement that led to significant improvement in our ability to realize complex systems. That's all I have.